Hello, in this video I would like to think through and talk about one of my absolute favourite derivations, and that is a proof of Euler's identity. And I'll just write that out, Euler's identity. And this is certainly one of the most famous equations in mathematics. It is what I would describe as a perfect example, perhaps even one of the most breathtaking examples of the concept or notion of mathematical beauty. And in fact, one could go on and wax eloquently for a very long time about what's so significant about Euler's identity and Euler's formula, and certainly also in relation to the derivation that we're going to consider in this video. But I will save that for the conclusion. Meanwhile, the first thing that we want to do in this proof is we want to expand out the Maclaurin series expansions for e to the power of x, sine of x, and cos of x. Now, I've already done that here in order to save time, for the sake of saving time, and trying to keep this video as short as possible. And what you see here is I've just pasted it onto the screen, the Maclaurin series expansions for e to the power of x, sine of x, and cos of x. And but before we get into that, maybe I'll just write down Maclaurin series just for reference. So it's Maclaurin series. And the Maclaurin series, actually we'll just first look at it, in that the Maclaurin series is basically, let's just write it this way, probably have enough space here. Maclaurin series p to the power p of x equals the sum or n equals 0 to infinity of f power of n times 0 times x to the power of n, and all that is over n factorial. And we can expand all of this out, and it looks something like this, where we have f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f prime, I'm running out of space, over 3 factorial times x cubed, and so on. That just goes on and on and on and on and on, right? So plus dot dot dot. This is the Maclaurin series, and the Maclaurin series, one could describe it really as a special case of the Taylor series. And if that doesn't mean anything, one could just think of the Taylor series really as a specific example of a power series. And if that still doesn't mean anything, we can simplify it even perhaps in a more intuitive sense, where the Taylor series really, one could think of it as basically an extension of the logic of approximating functions with polynomials at any point, i.e. taking n derivatives. Alright, so that's where this expansion comes from. This is a Maclaurin series expansion for e to the power of x, sine of x, and cos of x. And this is the first step in the proof of Euler's identity, or at least of the proof that we're going to consider in this video. Now, what's really striking when one considers the Maclaurin series for e to the power of x, sine of x, and cos of x is the early moments, one could describe it, of the emergence of a peculiar pattern. And that, let's just look at this, right? Well, e to the power of x, the expansion is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the power 4 over 4 factorial, and so on, right? There's infinitely many terms here. Just goes on and on and on. Likewise for the expansion of sine of x and cos of x. Goes on and on and on. Well, let's look at the expansion for sine of x, right? We've got x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial minus x to the power of 7 over 7 factorial. And what's worth highlighting here is just notice that the expansion for sine of x shows x to the power of n over n factorial for all the odd values of x, right? X cubed, x to the power 5, all the odd values. Well, what about the expansion for cos of x? Well, we have here, looks a little bit different, but what is so different about? Well, we have here x to the power of n over n factorial for all even values of x. And if that's not strange enough already, what is the let's just return to the expansion for e to the power of x, where we see both odd and even values of x, right? Like x squared, x cubed, x to the power 4, and that would just go on and on, x to the power 5 over 5 factorial, and so on and so forth. And I suppose if one doesn't understand what's really weird about this, or what's strange or peculiar, or makes one question, okay, what is going on? What something deeper is happening, but what is that? Is because the fundamental trigonometric functions, sine of x, cos of x, have absolutely no relation to e, the number e. But they come from these come from completely different areas of mathematics. And so to see that there's some strange, however tentative we might state this at the outset, some strange kind of pattern or connection makes one wonder, maybe there is something going on. And we can analyze this a bit more, actually. We can take another step. We can analyze this a little bit more by just adding sine of x and cos of x, right? If we notice that e of x, right, has 1 plus x squared, it has all these values, all the values of x, as we said. We see both odd and even values, whereas for the expansion of sine of x, we only see the odd values, and cos of x, we only see the even values. So what if we add sine of x and cos of x? Well, let's do that, just as a comparison, relative to the expansion for e to the power of x. Well, we have sine of x plus cos of x equals, okay, well, the first would be 1, and then in the logical order of things, be 1 plus x, right? They're positive, so it'd be 1 plus x, and then the next term would be x squared. You just follow the logic, so it'd be, and that's negative, so it'd be negative x squared over 2 factorial. And likewise, we have x cubed to be the next term logically, but it's negative, so we'd have negative x cubed over 3 factorial. And I'll just go on and write this out, right? So now we have x to the power 4 over 4 factorial, and that's positive. Likewise, x to the power 5 over 5 factorial is positive, minus x to the power 6 over 6 factorial, minus x to the power 7 over 7 factorial, plus dot dot dot, right? Because that just goes on. Well, now let's compare the expansion when we add sine of x and cos of x with the series expansion for e to the power of x. Well, one may have noticed that how sine of x plus cos of x is strikingly similar to the expansion for e to the power of x. In fact, they have the same terms. It is very, very clear. They have the exact same terms, right? 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Well, look at down here in magenta. We've got 1 plus x minus x squared over 2 factorial minus x cubed over 3 factorial, and so on. The only difference is the signs, right? Notice that in sine of x plus cos of x, we see the pattern: positive, positive, negative, negative, positive, positive, negative, negative. This is a very strange pattern, right? Why positive, positive, negative, negative is very strange. Whereas for in the exponential expansion, each term is just positive, right? Positive 1, positive x plus x squared over 2 factorial, and so on. So it's just positive. So, well, actually, to make things more clear, and when this is taught at undergraduate level, oftentimes one will see this technique to kind of highlight the pattern a bit more. One's lecturer will certainly do this. It's sort of a way of staggering or laying out all of the terms in these expansions. And I'm just going to copy this, and I'm going to paste it under the work we've already done. This is quite a common thing to do in this proof, to just highlight the pattern. And here we see this is the expansion that we've already considered of e to the power of x, likewise the Maclaurin series expansion for cos of x and sine of x. And all we've done is just spaced out the terms, right? That's all we've done here, to kind of match up with the expansion for e to x, just to see the pattern. You can see that they have, when we add sine of x and cos of x, we have all the terms in the expansion for e to the power of x, right? We've got 1 and 1, and we've got our x term here, we've got x squared over 2 factorial x cubed, right? And what I suppose this highlights is that there is indeed, we can be quite confident at this point, there is indeed a peculiar pattern that's emerging. And what emphasizes the peculiarity of it, or of what's in front of us, is that, again, sine of x and cos of x, they have no direct connection to e of x, to e to the power of x, or just to e in general. They just, the former come from trigonometry, right? The latter, the number e, comes from exponentiation. And so when we and so what we arrive at when we here is that when we add the polynomial representations of the two fundamental trigonometric functions together, as we see right up here, sine of x plus cos of x, when we add them together, we arrive almost exactly at the polynomial representation for e to the power of x. And needless to say, what this indicates is that there is something significant at work, and perhaps one might intuitively already suspect that something significant is at work, right? That we're beginning to touch on something quite deep and potentially profound. And really, it's at this point when I first learned this derivation that I began to get really excited, because this is really very curious. And so I guess the next question would be to ask, why this curiously similar pattern? Well, let's take another step. Okay, let's take another step in the proof. And to do that, what we want to do, and I'm going to scroll down here for a moment. Actually, I'll keep this on the screen, but I'll scroll down a little bit. What we want to do to take the next step is we want to consider the expansion of the function e to the power of I times x, where I is just the imaginary unit, right? So all we need to do here is substitute into our expansion. And if I'll just go back to white. So we have e to the power of I times x. And all we need to do here is essentially substitute into our expansion for e to the power of x, so that every time x appears, so like right there and right there, so every time x appears in this expansion, we want to substitute in I times x. And so the series expansion, in doing that, the series expansion looks something like this. So e to the power of I times x is going to be 1 plus, well, x, right? X appears here, so it's going to be I times x plus I, and I'm going to actually put it in parentheses, I times x squared over 2 factorial plus I times x cubed over 3 factorial plus I times x power 4 over 4 factorial plus, and I'm just going to go all the way to x raised to the power of 7, just for the sake of emphasizing the point, I suppose. I'm sorry, that's I. Getting ahead of myself. Plus, again, I times x, put it in brackets, the power of 6 over 6 factorial, and finally the last term, and actually that should be written like that, plus I times x in brackets, raised to the power of 7 over 7 factorial, and there are infinitely many terms, so that just goes on. Right. So why do this, I guess, is the obvious question. And the point really now is that because we can simplify this expansion quite easily, and to do so, actually maybe this serves as a good point of revision. To do so, we have to understand the value of the imaginary units I when raised to a power, right? And when we simplify all of this, it turns out that there's really yet another pattern in the signs, and we start to move toward the conclusion and or arrive at just a profound result. So the first step really is to we can simplify when we have to understand the value of the imaginary unit I when raised to a power. Well, okay, what is I? Let's write it. Where should I write it? Let's write it here. What is I raised when raised to the power of 1? Well, that's just I. What is I squared? Well, that is just -1. What about I cubed? I cubed is -I. -I. What about I raised to the power of 4? Well, that's just 1 equals 1. I raised to the power of 5 is just I. And I will only go to I to the power of 6 here, just to kind of highlight the fact that that it just repeats itself, the pattern repeats, because I raised to the power of 6 is just -1. And so you can see the pattern is just going to repeat, because I raised to the power of 7 is just going to be -I, and then we just go on and on. And so I'm just going to box that. Yeah, I'll just box this off. Just box this off, okay? Like this, and right, and so what we can do now in understanding the value of I when raised to a power is that we can start to simplify this expansion. So I'll just write it like this: simplify. So e to the power of I times x equals 1 plus ix plus, and I'm just going to write it this way to make the steps really explicit. I'm just going to distribute the index, right? So in this case, going to distribute like so. So we'd end up with I squared times x squared over 2 factorial, and I'm just going to do that for this entire series. So we'd have I cubed x cubed 3 factorial. I raised to the power 4. Why I'm doing it this way will hopefully be clear in a moment, just so one can see exactly what is going on. And I'll go all the way, just 2 more terms, I'm going to go all the way to I to the power of 7 times x to the power of 7 over 7 factorial, and of course that just goes on and on and on, infinitely many terms. Right, so we can continue the simplification now, where we, again, e to raise to the power of I times x equals, okay, well, 1 plus, well, what is I to the power of 1, right? So that's implicit here. Well, I to the power of 1 is just I, so that's just going to be I times x. What is I squared? Well, I squared is -1. So actually, it's not plus, it's going to be negative, right? It's -1, so it's going to be minus x squared over 2 factorial. What is I cubed? I cubed is -I, so it's going to again be -I times x cubed over 3 factorial. What is I raised to the power of 4? I raised to the power of 4 is just 1, so it's going to be plus x raised to the power of 4 over 4 factorial. What is I raised to the power of 5? That's just I, so it's going to, and it's positive, so it's going to be plus I times x raised to the power of 5 over 5 factorial. And I'll just go to the 6th. So what is I raised to the power of 6? It's -1, so it's going to be minus x raised to the power of 6 over 6 factorial, and plus, and that again just goes on and on, right? So I'll just stop here. So what is, I guess, really strange now in this expansion is notice that we have the similar sort of pattern of signs as we did earlier in when we added cos of x and sine of x, right? We've got positive, positive, negative, negative, positive, positive, negative, and if we were to add another term here, it would be negative, and it would just go on and on and on. And so here we've just reproduced that pattern, which is again quite peculiar. it indicates again, it reaffirms or reinforces that we're working towards something, but we're still not done, because we can rewrite e to the power of ix by separating out the imaginary terms and the real terms. Now if that doesn't make any sense, you think of it as we're factoring out the real terms and the imaginary terms, we're separating them, wherein it will look something like this: e raised to the power of I times x equals 1, and actually going to write it this way, put it in brackets, 1 minus, for all the reals, so for each term, for all the just real terms, so it would be 1 minus x squared over 2 factorial plus x raised to the power 4 over 4 factorial minus x to the power of 6 over 6 factorial, right? These are all the real terms in this series. Plus, and then we're just factoring out imaginary unit I. And so for all the imaginary terms, what does that leave us with? Well, I times x, right? So this can just be an x. Because if you were to use the distributive property this way, you would end up with what follows. So this would be I times x minus x cubed over 3 factorial, and maybe one can already notice what's happening here, because it's quite amazing. And next we have x raised to the power 5 over 5 factorial, and of course actually both of these would go on, so I should make that explicit like this. What do we have in front of us here? We'll notice that for the real terms, look, real terms, for the real terms, this is actually the Maclaurin representation of cos of x. And if that is not clear, let's go up to the Maclaurin representation for cos of x. It's right here in red. We have 1 minus x squared over 2 factorial plus x raised to the power 4 over 4 factorial, and so on. Well, look what we've got here. 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial. That is exactly what we have in our Maclaurin expansion, right? Look, we've got it right here. You can see it perhaps highlighted or featured more boldly in the red. So that's incredibly strange. But what about the imaginary? Well, notice too that for the imaginary terms, this is the Maclaurin representation for sine of x, and we've derived that. We've come to this result through the expansion of something completely unconnected to trigonometry, which is e to the power of I times x. And notice x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial. Well, let's look at the Maclaurin representation for sine of x, and we have them here now both on both the top and bottom of the screen at the same time. X minus x cubed over 3 factorial plus x to the power 5 over 5 factorial, and so on. So this is real, this is the imaginary terms, like this. And this is incredibly cool, right? Because it's I don't know, it's really actually quite difficult to describe. And in fact, mathematically we can prove these results, though when it comes to the final derivation of Euler's identity, Euler's formula, no one has actually really been able to explain it. But in any case, this is incredible, but we're still not done, because the awesome and awe-inspiring conclusion awaits. And but first we have to take note of something. If we agree, we have to think through some logic. If we agree that what we end up with here is a series expansions for cos of x and sine of x, we've just gone over that, we've looked at it, it clearly is, right, as discussed. In understanding that, like the series of cos of x and sine of x are real terms that we separated out, and the imaginary terms that we've separated out, right, the reals and the imaginary, that they have an infinite amount of terms, which we've talked about, right, at the very outset. They go infinite amount of terms. On the basis of that logic, we can say with great confidence that all the real terms, which we see right here, this expansion, which is plus, dot dot dot, goes on infinitely many terms, converges with cos of x. And similarly, all the imaginary terms, which we see right here, converge with sine of x. And we've just gone over that. We've just looked, we've compared them. And so if we agree with that point, well, we can rewrite all of this in a way that is just wonderful. Okay, and so, but let me say, so real converge, just as a note, converge with, actually, just make that a little bit neater, converge with cos of x, and the imaginary converge with sine of x, right. Well, let's think of it this way. Let's think of it this way. Let's mark this in red. Okay, right. So if what we have here is Maclaurin representation of cos of x, right? As we discussed, we can just cross this out. Really, we can write cos of x. And if this is the Maclaurin representation of what we have here in brackets, Maclaurin representation of sine of x. Let's write that, sine of x, right, equals sine of x. And in doing this, what do we have left over? And maybe I'll keep this in red color. Okay, well, we have e to the power of I times x equals, well, now it's cos of x, right? We're just rewriting this a little bit. It's cos x plus, well, if we use the distributive property like this, it would be plus I sine of x. And it just so happens that we have arrived at one of the most amazing results. If I can box this off, this is Euler's formula. And not only is this formula incredibly useful in that it helps us relate real numbers to imaginary numbers, and it also has many very useful practical applications, but with all of that aside, all of the practicalities aside, boy, is this so profound. It is so profound because it's such an amazing result, because not only have we found a relationship here very clearly between e, the number e, and two fundamental trigonometric functions, cos of x and sine of x. We've also found a relationship with all of that and the imaginary units I. In short, and this sentence should be italicized, we found a relationship with between some of our most important mathematical constants, all neatly presented in what is a rather beautiful and eloquent formula. And this is Euler's formula. But if that is not enough and we want to be greedy, there's still one more thing that we can do. And this is my favorite part. This is just truly astounding, and I may run out of space. Hopefully I can fit it all in here, because the next thing that we can do actually involves incorporating pi. In other words, we can now raise e to the power of I times pi, and the conclusion is truly magnificent. So let's do that. E to the power of I times pi. What does that leave us with? Well, equals cos of pi plus I sine pi. And one might think, okay, well, what's the big deal here? This just what we have cos of pi and plus I sine pi instead of cos of x plus I sine x of x, and you could say, okay, well, it's cool because we've got pi now involved. But think of it this way. Picture a unit circle. For the sake of space, I'm just going to draw it here on the right. Think of the unit circle. I'm not very good drawing circles usually, especially here, but okay. And so the unit circle, where this is obviously 2 pi, this is pi, and the value 2 pi of cos It's just 1, right? Sine equals 0, and that's cos of pi is -1, sine of pi is 0. Okay, well, we can substitute in the values here, right? Well, what is cos of pi, in other words? Cos of pi is -1, right? We're just referring to the unit circle. Cos of pi, -1. What is sine pi? That is 0, right? Well, that's just going to cancel out with I as well. And so what we end up with here is e raised to the power of I times pi equals -1. Or we could write e to the power of I times pi plus 1 equals 0. And there is what I described at the outset of this video as perhaps one of the perfect examples, most breathtaking examples of the concept or notion of mathematical beauty. That right there is Euler's identity. And if you've had enough, you can stop the video, but a few more comments now on this result, because this is really a breathtaking result. And in all the videos that you'll watch on this proof, and all the articles, formal or informal, that you'll read on this proof, and on Euler's identity and Euler's formula in general, one will not read and learn about this result without listening or reading comments by the author, listening to the author of the video wax eloquently about it, because it is breathtaking. And what we see here, among other things, are not only as highlighted or noted earlier, the fundamental mathematical constants, each again from completely different areas of mathematics, all linked together. More than that, I think it's fair to say that this equation represents something incredibly deeply profound. For example, Richard Feynman, who is one of my favorite physicists and one of my personal idols, who among many others inspired me to study physics and dedicate my life to physics, he once called the equation our jewel and the most remarkable formula in mathematics. But if that's not enough, mathematics professor Keith Devlin has been quoted as describing Euler's identity as being like a Shakespearean sonnet that captures the very essence of love, or a painting that brings together the beauty of the human form that is far more than just skin deep. Euler's equation reaches down into the very depths of existence. And this might seem like hyperbole, but Devlin's description really does capture the essence of what is so significant about the theorem, I think, as possibly one of the most beautiful discovered by human beings. It is so profound that that I would describe it in my own words as possibly one of the genuinely deep historical human artifacts. I would certainly place it, I think, as I mentioned at the outset, as alongside Maxwell's equations and others. I just think it's astounding, and it's just because when we think about it, this particular theorem and its derivation, this derivation is especially, I would describe as historical and a more immediately intuitive proof. You know, when we think about what we have in front of us, it offers a great depth to the human project, the scientific project, and in that what we have in front of us here links together not only the fundamental mathematical constants, capturing the relationship between calculus, which we get our series expressions, and trigonometry and algebra. I would describe it as historical in significance because it, and I think a lot of people would agree. You know, you hear people describe it in the same way as this result representing a moment in which human beings have glimpsed at something deeper with respect to truth in relation to nature. There's, I would, you know, it's a bit interesting in that there are people out there, and perhaps misguidedly, argue that this theorem proves the existence of things like God and just all kinds of stuff, and I don't really subscribe to any of that personally. But I would say that it is not unreasonable to suggest that this mathematical conclusion is evidence of the objectivity of mathematics in relation to nature. I would certainly go so far to say that that there's something very, as an example, a piece of evidence that suggests that there's something fundamentally objective about mathematics, that expands outside of the realm of purely human creation. I would perhaps go so far to say that that mathematics is not purely human creation or narrative or just another story or anything like this, as some sort of meta narrative. That it is that mathematics is there to be discovered in nature, and there's something very fundamentally objective about that, and something very Pythagorean even, if one wants to go that far back. So this is the result. This is Euler's identity, and one could go on and on and on and on and on and talk about it and just think about it and philosophically and all these things. But yeah, so that is it, and it is truly a significant result.